we're going to take a look at the basis for all trigonometry, and it's called right angle trigonometry. Now it's called right angle trigonometry because everything we're going to look at is going to be based off of a right triangle. Now of course a right triangle is a triangle that has one angle being 90 degrees, which leaves us two other angles that can change. Well, there's something really interesting about right triangles. If we call this angle, any angle, theta, as long as I draw the same angles in a triangle, it doesn't matter how big it is. I'm going to make one that say, let's make it a little bit smaller. Well, let's say it's still a right triangle, and this angle is exactly the same as this angle. If I were to label these sides A, B, C, and I don't know, D, E, F, something really interesting happens. If we do the ratio of some sides, now ratio just means the fraction of, so let's say if we do the ratio of B divided by A. Now if I do the exact same ratio on this one, that would be this angle and this angle, we will always get the same answer as long as this angle here is the same. So it's amazing. So if I did like C over A, that would be the hypotenuse over this side. That would be the same value if I did the hypotenuse over this side. So this would be the same as F over D. So it doesn't matter how big the triangle is. Now, it does matter what this angle is, right? If this angle changes, this angle theta, like if I were to change that angle and make it, say, smaller, something like this, and we call this over, we have G, H, and I. Now that wouldn't be the same. Now notice I didn't label that as theta because it's not the same value. Now this wouldn't be true, right? We did B over A, so this side to this side. If we did H over G, we wouldn't get the same answer because this angle is different. So really, this one angle defines the entire triangle, right? So since this one's 90 degrees, whatever this angle is, we also know what this angle has to be because all the angles of a triangle add up to be 180 degrees. So if this is 90, these two have to add up to be 90. So this angle up here has to be 90 degrees minus that angle. And that's true for all of our triangles here. So we end up with this really neat, interesting fact about triangles, right triangles, to where the sides, the ratio of the sides stay the same no matter how big the triangle is. Now if we take a look, let's just take a look at our first triangle here. Let's get these out of here. If we just take a look at our first triangle, and just to clean this up a little bit, let me get this out of here. We have three sides, so how many different ratios could we do? How many different fractions could we do? Well, we could definitely do B over A. I think that was the first one we did. We could do B over C. We could do A over C. What else could we do? Well, we could take all these and we could do the reciprocal. The reciprocal of them, I could do A over B, C over B, and C over A. Now notice those are the only possible fractions we can make out of the three sides of these triangles. So we have a total of 6 possible ratios we can get from one triangle. Now this is where we're going to define what we call our 6 trig functions. Now our trig functions are really just give us the value of this ratio depending on what this angle is. Because remember, this angle is the only thing that defines these ratios, as long as it's a right triangle. So here's what we're going to do. I'm going to go ahead and erase these real quick because those were just kind of random. We're going to define 6 trig functions, and I'm going to give them their full name first. We're going to define what's called, not if I write it like that. We're going to define what's called our sine function, cosine function, tangent function. Now the reason I'm going to write it like this, over here we're going to define our cosecant function, secant function, and cotangent function. Okay, these are the 6 trig functions we're going to be dealing with all throughout trig, so we got to get really familiar with them. Now, what are each one of these? Well, each one of these represents one of those 6 ratios that we just talked about. So the way we actually write these as functions, and what I mean by a function is the ratio, let's say B over A, is going to change when theta changes. So if we know what theta is, we'll be able to figure out what that ratio is. So in this case, the way that we write this is we're going to abbreviate all these with a 3-letter word. For sine, it's just sin. And now we got to plug something into this, kind of like if we have a square root, right? We got to plug something into it. We're going to plug something into that, and what we plug in is the angle. So we do the sine of theta. So there's our first trig function. It's the sine function, and we're taking the sine of theta. That's the way you would read that. Now, the ratio we have for the sine, if we're looking at our angle, the side opposite from it, so if you go straight across, that's the opposite side, and this side is called the hypotenuse. So we generally say that the sine is the hypotenuse. The sine function is the opposite side over the hypotenuse. Our next function, the cosine, we abbreviate COS, or cos. So this would be the cosine of theta. So here we're plugging in our angle. We get a different ratio for here. If this is our angle theta, the cosine is what we call the adjacent side. So that's the angle touching it. I know, or the side touching it. I know C is, but that's our hypotenuse. So it would be the adjacent over the hypotenuse. Adjacent over the hypotenuse. And our last one in the first column here is our tangent function, which we abbreviate tan, T-A-N. I guess it looks like an O. It's a T-A-N for tangent. So the tangent of theta was going to be the opposite side over the adjacent. Adjacent. Okay, now we generally, when we think about these are our 3 main trig functions. Now the other ones, people tend not to memorize those as well, because as long as you know these 3, you can figure out what the other ones are. So the reason I wrote them in this order is because if we go over here, the cosecant is abbreviated CSC. So the cosecant of our angle theta, it's just going to be the reciprocal of the sine function. So if we just flip this one over, that would be our hypotenuse over the opposite. The next one, secant, is going to be the reciprocal of cosine, so we abbreviate secant SEC. So secant of theta is going to be the hypotenuse over the adjacent. And our last one, the reciprocal of tangent is going to be cotangent. We abbreviate cotangent, COT. So this is the cotangent of theta. Is going to give us the adjacent over the opposite. Okay, these are our basic definitions. You've got to know these. Get yourself some flashcards, start memorizing them. There's a lot of little mnemonic techniques out there from the internet that you can learn, like Sucatoa and a whole bunch of other ones that you'll probably run into if you're looking for them. But you got to memorize these no matter what you do. These are our basic definitions. So how would we use these? Well, let's take a triangle over here. Let's say we have a right triangle, and here we have some angle theta. And let's say I gave you a couple of sides. Let's say if I gave you a side 3, 5. This is going to happen a lot throughout this kind of section. If we have 2 sides of a right triangle, how do we find the third side? Well, to find the third side, of a right triangle, use the Pythagorean theorem. Okay, so hopefully everybody remembers our Pythagorean theorem. It's a squared plus b squared equals c squared. Now, on the label of our triangle A, B, and C, it really doesn't matter. I'm actually going to refer to this. It really doesn't matter which sides we call A and B, but what has to be the side that's on the side all by itself, this one, the c squared, that has to be the hypotenuse. So in this case, we don't know what the hypotenuse is, so let's put a letter there. So when we plug in what we know, we have 3 squared plus 5 squared is equal to c squared. 9 plus 25 is c squared. So what's that? 34 is c squared. So if we take the square root of both sides, we get plus or minus square root of 34 is what c is. Remember, anytime you take the square root, you do get a plus or minus. However, we're talking about the side of a triangle. So a side can't have negative length. So we're just going to take the positive square root there, and we're going to call this here the square root of 34. Okay, so given that's our three sides of the triangle, I'm going to back us up over here just so we got a little bit more room. We can refer to that triangle there. And I'll leave this up for a second. I'm going to say, let's find the value of all 6 trig functions for this triangle. Okay, so if we're looking at this triangle here, and I said find the trig value of all 6 things. So the 3 things that we're going to start out looking for are our 3 main ones. We're going to look for the sine of theta, cosine of theta, and the tangent of theta. Again, you got to memorize these. So if I'm looking at the angle theta here, I know the sine function is the opposite over the hypotenuse. So the opposite would be 5. The hypotenuse would be 34. So the sine of that angle theta is opposite of, the opposite over the hypotenuse. There we go. Now we'll talk about that answer in just a second. Let's keep going though. The cosine. For this angle theta here, the cosine is the adjacent over the hypotenuse. So the adjacent is 3, the hypotenuse is still 34, square root of 34. So we get 3 over the square root of 34. And the tangent, again, we know that the tangent is the opposite over the adjacent. So for this triangle, the opposite side is 5, the adjacent is 3. So we get the ratio of 5 over 3. Okay, now that we have these 3, the other 3 trig functions are really easy to know as long as you know which ones are the reciprocal. The reciprocal of sine is cosecant. So that's going to be the square root of 34 over 5. The secant is the reciprocal of cosine, which is going to be the square root of 34 over 3. And the reciprocal of tangent is cotangent, so that'll be 3/5. Okay, so we found the 6 trig values of this function for this triangle right there. Now, as far as your textbook is going to go, and most textbooks that you're going to read aren't going to like this answer here very much, because we were told in the past that we needed to get rid of radicals in the denominator. So make sure you remember how to do this. To rationalize something like this, all you need to do, I got blue right here. I think this works. Let's see. We're going to multiply the top and the bottom by the same square root that's on the bottom, so square root of 34. And of course, on the top, we just multiply straight across. We get 5 square roots of 34. Square root times itself, well, that makes it squared, so it goes away. So that's most likely the answer you would see in the back of the book. So make sure that you do remember how to rationalize things in case somebody asks you to do that. All right, so finding the 6 trig values are very important for just about any triangle. Now we're going to run into a couple of special triangles out there that we're going to need to kind of just memorize. That are going to be very, very important for us. Let's take a look at our first that we're going to call 30, 60, 90 triangles. Now, good news and bad news here. We're going to memorize this as 30, 60, 90 triangles, but when we put the angles in, we're actually going to put in the radians for this. So a 30, 60, 90 triangle, of course our 90 degrees is going to be right there. We're going to have a pi over 3, which is 60 degrees, and pi over 6, which is our 30 degrees. Now, since we know exactly what these angles are, we can actually figure out exactly what the sides are here. The sides on a 30, 60, 90 triangle are 1, 2, and the square root of 3. So you got to remember these numbers. Now, an easy way to remember this is the biggest number, of course, goes on the hypotenuse. And 2 is actually bigger than the square root of 3, so 2 is the hypotenuse. The smallest number, which is 1, goes across from the smallest side, or the smallest angle. Now remember, this one here is 60 degrees, this one is 30 degrees, so the 1 goes there, and the square root of 3. Now, a student years ago actually told me an easy way that she remembered it. She just remembered that the square root of 3 went across from where the 3 was. Kind of easy way to remember that, I guess. The other triangle that is going to be extremely important for us to remember is the 45, 90 triangle. So in this case, draw another triangle. That's a horrible triangle. All right, there's our 90-degree angle. So 45 degrees is pi over 4 in radians. Now the three numbers we want for this is going to be 1, 1, square root of 2. Now these sides are easy, of course. Since these angles are the same, the sides opposite have to be the same. So those have to be 1, which means this is the square root of 2. All right, so let's take a look at all 6 trig functions for these two special triangles, because we're going to run into these quite a bit throughout the semester. So if I said, what is the sine of, say, pi over 3? We're going to do just a couple of each triangle. So the sine, remember, is the opposite over the hypotenuse. So looking at pi over 3, we go to the opposite over the hypotenuse. So that gives me square root of 3 over 2. If I said, what's the cosine of pi over 3? Well, again, here's our pi over 3. Cosine is the adjacent over the hypotenuse. So that would be 1/2. And I don't know, let's do something different. What if I said, what is the sine of pi over 6? Okay, we find pi over 6. Right there's pi over 6. The sine is the opposite over the hypotenuse. So that's the opposite over the hypotenuse. So that would also give us 1/2. So a good practice, what you should do is make sure that you can find all the trig values for the kind of, we call these known angles because we deal with them so much. Or if I came over to this triangle and if I said, what is the tangent of pi over 4? Well, we find the pi over 4. Now notice we have 2 of them, but we would get the same answer, right? Because the tangent is the opposite over the adjacent. So that would be 1 over 1, which of course is just 1. If I had picked this one, then this would be the opposite. That would be the adjacent, but you get the same answer, right? So what about, let's do a hard one. Let's do the secant of pi over 4. Now, the way that most students tend to remember this is they don't really remember the secant. Now, you're welcome to, and I actually highly suggest that you do it, but I find that most students don't do it that way. They say, you know what, secant's related to the cosine. Now, I know the cosine, so if I look at pi over 4, and I know the cosine is the adjacent over the hypotenuse, so I know the cosine is 1 over the square root of 2, right? The adjacent over the hypotenuse. I know the secant is the reciprocal of that, so that would be the square root of 2 over 1, or just the square root of 2. All right, I highly suggest you being able to scribble down these triangles really, really quick. It's really helpful on a test for a lot of things that we're going to do. You're going to want to be able to draw these triangles so you can refer to them as you go. So get really good. Every time you sit down to do your homework, see if you can write these down to use them as reference. All right, let's take a look at a few more things about our right triangle trigonometry. Because we can see that a lot of the sides are related, we end up with a lot of things that are called identities. Now, an identity is a word that you're going to hear a lot in math classes, but all identity means is a true statement. This is just a so 3 equals 3 is a true statement. You know, 5 equals 2 plus 3. That is a true statement. So these all can be considered identities. Now, we have some identities in our trig functions, and we kind of just talked about one here. We know, let's talk about these are called the reciprocal, I misspelled identities. There you go. The reciprocal identities are just, we know that half of our trig functions are the reciprocal of the other half. Now remember reciprocal, if I have A over B, the reciprocal of that is just flip it over, right? So I know that we'll do them the way that we know them. We know that the cosecant is the reciprocal of sine. Well, if I have the sine of theta, remember that's a sine of theta over 1, so the reciprocal of that is 1 over the sine of theta. We know the secant of theta is the reciprocal of cosine, so 1 over the cosine, and we know the cotangent is the reciprocal of tangent, so 1 over tangent. Now, since reciprocals are reciprocals of each other, right? Kind of like what I put here a second ago, A over B is the reciprocal of B over A, or I could say it the other way around. B over A is the reciprocal of A over B, which means we could also write these the other way around. Technically, the sine of theta is the reciprocal of the cosecant. The cosine of theta is the reciprocal of the secant. And tangent is the reciprocal of cotangent. Okay, so you do need to know how these pairs relate to each other, which ones are reciprocals of each. It kind of makes some things that we're going to do in the future a little bit easier. All right, let's keep going. Now, there's some other identities that we can come up with that end up being quite helpful. The tangent and cotangent identities. Now, the tangent and cotangent identities is kind of this idea here. Watch if I took the sine of an angle and divided it by the cosine of an angle. Now I'm going to go back to our definitions just to kind of make this easier to see. Now it's going to be a little messy at first. Remember we said that the sine of theta was the opposite side over the hypotenuse, kind of abbreviating there. We said the cosine was the adjacent over the hypotenuse. So this is just the sine of an angle over the cosine of an angle. Well, this is a fraction divided by a fraction. So we know when we divide fractions, we multiply by the reciprocal. So the top stays the same. And I multiply by the reciprocal of this. So this is the hypotenuse over the adjacent. Notice here our hypotenuses would reduce, and if we multiply straight across, I get the opposite over the adjacent. Now, by definition, that's exactly what we called the tangent function. So here, you can see that we can actually represent the tangent function. The tangent of theta can be represented as the sine over the cosine. Now, since we know that the tangent and cotangent are reciprocals, we could do the same thing if we wanted to and show that the cotangent is just the reciprocal of this, which would be the cosine over the sine. All right, so there we can see that we can actually rearrange both our tangent and cotangent in terms of just two other trig functions. Let's take a look at another identity. This is called our the Pythagorean identity. Now, of course, the Pythagorean identity is going to be based off of our Pythagorean theorem. So let me do this real quick. I'm going to draw a real small triangle here. Let's call that the angle theta. Excuse me, let's do A, B, and C. So according to this triangle and the Pythagorean theorem, I'll bring it up here. I know that A squared plus B squared is equal to C squared. Now, since it's an equation, you should agree that I'm allowed to divide through by anything I want as long as it's not 0. Well, I know C is the length of the side of the triangle, so I know it's not 0. So I'm going to take this equation and I'm going to divide everything by C squared. Don't ask me why, I'm just doing it. You'll see in a second how this is going to work out for us. Okay, now I'm going to rewrite this since for the fractions on the left-hand side, you can see that both the numerator and the denominator are being squared, so I can actually rewrite this as A over C. And write that as B over C squared, and of course on that side we just get a 1. Excuse me. All right, so what did that get us? Well, we're supposed to be talking about trig here, so if we now take a look at our triangle, and I look at the ratio of A over C, according to this, A over C would be the sine of this angle because A is the opposite of theta and C is the hypotenuse. So I can write this as the sine of theta squared. And guess what? B over C would be the cosine because for theta, that would be the adjacent and that's the hypotenuse. So this is the cosine of theta squared is 1. Now this is a pretty interesting result. It says if you take the opposite side of a triangle divided by the hypotenuse, whatever number that is, you square it. You take the adjacent side of a right triangle divided by the hypotenuse, whatever that number is, you square it. Add those two values together, you're always going to get 1. Pretty interesting. Now, we are going to use a little bit of a shorthand here when we're applying powers to our trig functions. And what we're going to do is we're actually going to put the power on the trig function itself. It's just a neater way to writing it instead of writing it like this. See, if I were to just get rid of the parentheses and write it like this, don't write this down, this is wrong. This is saying that we're squaring the angle. So if the angle was 30 degrees, we'd be squaring 30 degrees. So we don't write it like this. We actually put the power on the trig function. So the way we would actually read this is sine squared theta plus cosine squared theta equals 1. This is our first Pythagorean identity. We actually end up with 3 of these, and I'll show you where the other 2 come from in just a second. Okay, so this is our first Pythagorean identity. You do need to know it, it's super important. Now, we get 2 more. Now, the reason we get 2 more identities is because at this step right here, I randomly divided through by c squared. I could have divided through by a squared or b squared. And if I had done either one of those 2, we would have gotten 2 different sets of identities. Now, I'm going to show you real quick, because I'm out of board over there. I'll go this way. If you memorize this one, you can always figure out what the other 2 are. So I'm going to start with this one. I'm going to start with sine squared theta plus cosine squared theta is equal to 1. If I take this equation, and I'm going to do 2 different things. I'm either going to divide through by sine squared, or I'm going to divide through by cosine squared, because that's what I have, sines and cosines. So if I take this equation, if I divide through by, I don't know, let's do cosine first. Cosine squared plus cosine squared theta over cosine squared theta, 1 over cosine squared theta. Now again, I'm going to do the same trick that I did over here. Since the top and the bottom are both being raised to the same power, I can put that in parentheses. So this ends up being sine of theta over cosine theta squared plus, well, this is just 1. And since I can write 1 to any power, I can write this as 1 over the cosine of theta squared. Now, using a few of the identities we just took a look at, I know sine over cosine, that gives us the tangent. So this would be the tangent of theta squared plus 1 is equal to, and from our reciprocal identities, I know 1 over cosine is the secant of theta. Now again, we generally don't write powers on our trig functions like that, so I'm going to bring it inside and write this as tangent squared theta plus 1 is equal to secant squared theta. All right, that is our second Pythagorean identity. I'm actually going to squeeze it down over here. I'm going to take the bottom off this box real quick. I'm going to put them all in one box. So here we said this one was the tangent squared theta plus 1 is equal to the secant squared theta. Okay, now you can hit pause if you need a second to copy this down, but I'm going to erase this basically and do the exact same thing that I just did. Maybe skipping a step now that we've seen it. But instead of dividing through by cosine squared, I'm going to divide through by sine squared. Okay, what does that give me? Well, of course, this is 1 plus. Now, I'm going to kind of skip a step here because hopefully we can see where this is going. These are both being squared. So what is cosine over sine? Well, cosine over sine is cotangent, and of course, we're going to be squaring this. So this is cotangent squared theta. And this is going to be 1 over sine, which is cosecant, and then we're going to square it. So this is going to be cosecant squared theta. So there's our third Pythagorean identity. This one is, we got as 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, there are your 3 Pythagorean identities. Since there's so much memorization in trig, generally what I suggest students doing, instead of memorizing all 3 of them, memorize the first one, and remember to get to the other 2, all you gotta do is either divide through by sine squared or cosine squared. All right, we're gonna take a look at one more set of identities. And I guess I'll go right here. Let's take a look at one more set of identities. These are called the cofunction identities. Now, we can see really quick why these cofunction identities work. If we take a look at our triangle that we drew earlier today, now remember, if this is 90 degrees and we know what this angle is, then I know this angle up here has to be 90 degrees minus that angle, or 90 degrees or pi over 2, that would be the radians. Because think about it, if this was 50 degrees, right? Then to get this angle, of course, that would be 90 degrees minus 50 degrees, so that would have to be 40. Okay, so if we take a look at this and theta, it's crappy theta, I'm gonna do it again. We have a theta here. Now watch, I'm just gonna label the sides kind of like how I've been doing today, A, B, C. If I did the sine of theta in this case, the sine of theta would be the opposite over the hypotenuse, which would be B over A. Now, if I did the cosine of 90 minus theta, that would be the cosine of the opposite angle of that. What would we get? That would be the adjacent, that's a C, I messed up, opposite over hypotenuse. I said adjacent, I made a mistake. All right, so here we'd have what? The adjacent over the hypotenuse, and we'd also get B over C. Right, because if we switch angles, we switch which sides are opposite and adjacent. So if we do the sine of one angle, we'll get the same answer if we do the cosine, the cofunction, of 90 degrees minus that angle. So the way the cofunction identities are written, get this out of here. If we said the sine of some angle would be the cosine of 90 degrees minus that angle. Now we could also say that exactly the other way around. The cosine of an angle would be equal to the sine of 90 degrees minus that angle. So we have the sine and its cofunction, cosine. So it works the same way for if we have the secant of theta, its function would be, the cofunction would be cosecant. Or the cosecant of theta is equal to the secant of 90 degrees minus theta. And the last co-pair that we have is tangent. So if we have the tangent of theta would be the cotangent of 90 degrees minus theta, or the cotangent of theta would be the tangent of 90 degrees minus theta. So it's nice to know this relationship between the functions and their cofunctions, but to be honest, these are relationships that we don't use too much, but you do want to try to commit as much of this to memory as possible. There's a huge amount of stuff that we covered today. Almost all of this needs to be memorized, so make yourself some flashcards so you can just sit there while you're doing whatever and flip through the flashcards to start memorizing all this stuff, because trig is all about memorization.